Welcome back, chemistry fans. Today, we are going to do a warm-up that needed to be corrected. It is for day number 35, I believe. Let me check that. Yeah, day number 35. So let me jump into the work here with you, and let's share screen, and then we can go over these sharing of the bonds and anti-bonds, because that's the part that I'm sure screwed up many of you if we watched the videos and did not include anything new about it. All right, so let me blow this up so we can see what we're talking about, and let's get into it. All right, so first, what type of hybridization? Well, to know the hybridization, you're going to have to do some previous work. You're going to have to draw the structures. Now, I have done this before, but let's go ahead. So I know what this is just off the top of my head, but I'm going to do 1 minus half so that you guys can start to see how we develop this, because this is important that you go through the work. You don't just Google your answers. And so there are 4 materials. They each want 8. That is a total of 32. The halves, they are 4 of them. They each have 6. That is a total of 24. The difference between them, it is 8, meaning that there are 4 bonds. The sulfur is the first element, so it sits in the middle, and then it has oxygens around it, and you can simply put one of them as a double bond. It doesn't matter where that double bond is. This is called resonance structure. Now, the type of hybridization is that you got to count those number of bonds, and the first bond is always an S, and then you would have a P. So I would have one S, I would have one P, here's a second P and a third P. So we would have sp3 as the type of hybridization. So it's just a matter of counting them and then kind of going back to what we did with the electron configuration. So that's where the hybridization occurs for this type of bond. Now we're going to go into something called formal charge. Formal charge has a formula, and that formula is valence electrons minus the number of bonds minus the number of electron pairs. All right, unshared electron pairs. So what we do then is that we compare who has the lower number on whole, and that's the one that is the more favored structure. So here we go through this. So for the hydrogen, it has 1 valence electron. It has it has 1 bond, and it has no unshared pairs of electrons. So that is a total of 0. Now, for both of these oxygens are going to have the exact same. They both start with 6 valence electrons. They have 3 bonds. Now, what's not shown is that there are 2 unshared pairs of electrons. And so what we get then is a total of 1 for that. Do the same over here, and it would be a 1. And my hydrogen over here would have the exact same value of 0. So I have a 0, a 1, a 1, and a 0. Now we're going to compare that. Whoever has the lower numbers overall, that's the one that you're going to go with as the more favored. So what we have here, unfortunately, is not a double bond, and so we're going to have a lot more unshared pairs of electrons. Now, nothing changed for my hydrogens. The math on that one is still going to equal 0. It is 1 valence electron minus 1 bond. There's no unshared pairs of electrons. Now, these oxygens, though, are going to be different. They have 6 minus the 2 bonds minus the 4 electrons. That's 0. Okay, and then that's going to be the exact same for this one. So what you notice is all 4 of these values are 0, as opposed over here, we have a 0, 1, 1, 0. So this is my more favored structure because all of the values on the whole are smaller, closer to 0 than they were on the other. So that's my favored structure. That is the correct way to draw the structure of H2O2. All right, label the sigma and pi bonds. Sigma bonds are always the first bond. So these are sigmas. And then up here, my first bond is a sigma, and these 2 are my pi bonds. So always the second and the third bonds are called pi bonds, and that's just something that we need to get used to. Okay, now we're going to do He2 over here on the right, and we're going to do O2 over here. And so we fill these in based on how many total electrons they have. Oxygen, it has 8 electrons. So if we were getting here with our structures 1, 2, 3, 4, 5, 6, 7, 8. And the exact same would be the case. Those are our orbital diagrams. Now, how does it work with the bonding? So you fill from lowest to highest. Anytime we have antibonds, that means these are not electrons that bond. So we'll put 1, 2, 3, 4. Notice there's 1, 2, 3, 4. So this is not where a bonding is occurring in the first energy level. And that explains the fact. There is 2 electrons that are pushing against the 2 that want to be together. The same is true for the 2s. So the 2s electrons, there is not bonding that's going on. Now we go from lowest to highest. We always fill lowest to highest, and we have a total of 8 electrons that we can put in here. 1, 2, 3, 4, 5, 6, 7, 8. Now, because there is going to be some of these 2 electrons that are going to push against those, what that tells us is I have a double bond that is in between the oxygen. This is going to occur. Now let's go and look at helium. If I look at helium, helium has its element number 2. It has 1, 2. It has 1, 2. And if we were to fill this in, here's 1, 2 here. Those are the bonding electrons. The anti-bonding electrons are down here, and they cancel each other out. That's the reason why helium does not form a diatomic molecule, but oxygen does. All right, so this is our answers that are going to work for us with the warm-up for day 35. Thank you very much. Talk to you again soon. Bye-bye.